Okay, so we're back again. We're going to hopefully finish off the packet with this last video. We're going to talk about temperature and density, okay? So pretty much common sense stuff just to finish it off, all right? So this kind of reminds me of a movie. I don't know if you ever remember, Sylvester Stallone was in it. I think it's called, and Wesley Snipes, yeah. I think it's called Demolition Man, right? So it's set in the future, and in the future, there's only one restaurant, right? It's Taco Bell. And they say, oh, Taco Bell has won the franchise wars, right? There were a bunch of different restaurants, and then they had this battle, and one ended up the winner, the last remaining restaurant. There's a similar kind of thing going on with temperature scales. It turns out 100 years ago, there were maybe a dozen temperature scales. Yeah, everyone had their own scale. Some were good, some were not so good. And over the years, they've whittled down the number of scales, and there's now only 3 left, all right? So we're nearly to the final point of 1 scale, but right now we have 3, okay? Now, these are the 3 inventors of the scales, okay? They're all Scandinavian, it turns out, because I guess an important question in Scandinavia is it cold outside? And you say, yes, and well, how cold? So, 3 temperature scales, and they're actually in chronological order. This is the oldest. This is kind of the middle-aged scale, and this is the youngest scale. Okay, these are the inventors. This is an artistic impression of the person because it's so long ago. This person's image has been lost to history. It's kind of like a picture of Jesus or something. No one knows what this person looks like. It's a best guess. All right, so that's actually Fahrenheit. Make sure I get his name right. He has, of course, the degrees Fahrenheit scale. Sometime later than Fahrenheit came, you may know, Celsius. He has the degree C scale. Okay, and then later still, and this is actually a photograph. That's not an oil painting. This is an actual photograph in the realm of photography. This is Kelvin, Lord Kelvin, right? Big K. No degree sign for Kelvin. We'll talk about why later. Okay, so 3 temperature scales in common use today: Fahrenheit, Celsius, and Kelvin. Okay. Now, Fahrenheit isn't really used in science, so we'll concentrate more on these 2. Okay, we'll talk about this a little bit more later, but Celsius and Kelvin, they are actually related quite closely. Okay, now it turns out that when you set up a thermometer, you need endpoints, right? Okay, you need endpoints. And if we look here, we can see that, for water, Celsius was smart. He said 0 degrees C was the freezing point of water, and 100 degrees C was the boiling point of water. So it's real easy to set up a Celsius thermometer. You just get your glass tube with your mercury alcohol in it, right? You put it in a glass of ice water, which is water and ice at 0 degrees C, right? And then you mark off, right? And then you put it in the boiling water. Heat the water up, it boils, water and steam, right? Mark it off, that's 100, and mark 100 divisions between, right? So the fact that water is very, very available makes the Celsius scale a very good centigrade scale. That means it's got 100 divisions for calibration, okay? All right, so there we see there. So there's our Celsius scale, 0 degrees C, 100 degrees C. That's how you calibrate the scale. Obviously, now, interestingly, it's degrees C, right? Because 0 degrees C is not the lowest possible temperature. There are lower temperatures still. So when we go down here, we have negative values. You can get negative values on any degree scale. If it's degrees Fahrenheit, degrees Celsius, there are negative numbers. So 0 isn't the bottom, right? 0 is not the bottom. Okay. So you can have negative numbers. Now, that's fantastic, right? But here's the thing, Celsius and Kelvin actually overlapped a little bit in their lifetime, right? And Kelvin really liked how Celsius used the boiling and freezing point of water to set these 2 points, right? But he was like, well, why don't you just make 0, 0? So he said, what's the lowest possible temperature you can get to? And it turns out you can get down to minus 273. And at 273, that is actually a minimum because no atoms are moving at minus 273 degrees C, and temperature is measuring atomic movement, right? So everything's frozen solid at minus 273. There is a bottom, right? There is a bottom of the well. It's minus 273, and that's called absolute zero. Sounds like a vodka, but it's no, it's absolute zero, right? And Kelvin said, well, I'm going to make my bottom, your minus 273, my zero. And that's why Kelvin has no degree sign, because zero is the lowest number on the scale, right? And if you think about it, there was from 0 down to minus 273, that's 273 units. And Kelvin kept the step size the same, right? So he said, oh, I'm going to put 273 units between 0 and the freezing point of water, and then 100 between boiling and freezing, right? So if you notice, there's 100 between there and there. There's 100 between there and there. There's 273 between here and here, okay? So if you like, it's two ladders with identical gaps between the rungs. It's just that one ladder is kind of in a hole, all right? And that's why Celsius and Kelvin are related. They're related by a difference of plus or minus 273, which we'll get onto. All right. So convert it between the scales. Okay. So key point number one: scales are offset by 273 units. Okay. And then, so that means, if you like, the step size is the same. What that means is, therefore, a difference of 100 degrees C equals a difference of 100 Kelvin. There's 100 Kelvin between boiling and freezing, 273, 373. There's 100 Celsius between boiling and freezing, 0 and 100. Okay, so the step sizes are the same. It's just that the ladder is one, like I said, one's in a hole, one goes kind of underground, goes minus, which will be Celsius. One starts at ground level, which will be Kelvin, if you like. All right, does that make sense? No, kind of. All right, so you get the idea, though. The scales are offset by 273. Kelvin starts at true zero. Celsius starts at minus 273. But a difference of whatever you measure, right? A difference of 100, difference of 200, it's the same distance on both scales, all right? So because of that simple difference of 273, all you do, and it's 273.15 with the sig figs, all you do, just remember this: Kelvins are bigger, okay? Kelvins are bigger. If you go back, 0 degrees C is 273 Kelvin, right? So I'm going to just add 273. Every time I go across, I just add 273. So Kelvins are bigger by 273. We go to the nearest whole one. You know, that's okay, but add 273 to get Kelvin, subtract 273 from Kelvin to get Celsius, okay? So figure it out, right? What's 50 degrees C in Kelvin? What's 200 Kelvin in Celsius? All right, pause there, work it out. Okay, back. So 50 degrees C in Kelvin, what did we say? Kelvin's always the biggest number, right? So 50 degrees C plus 273, Kelvins are always bigger, equals 323. Make sure I get it right. Fair enough. 200 Kelvin in Celsius. Well, 200 Kelvin subtract 273 minus 73 degrees C. Let's look at that on our scale here. There's 50. There's 323. There's 200. There's minus 73. Okay, so you can just draw across if you want. All right, so that's nice and easy, right? Hopefully. Okay. Now, why did Fahrenheit not fare so well in this kind of scientific battle? Okay, why don't we use Fahrenheit in science? Well, it's kind of interesting. It turns out that Fahrenheit did actually do a centigrade scale, okay? So if I do my Fahrenheit here, I do my Celsius here, right? So 100 degrees C, 0 degrees C, that's the freezing point of water, that's the boiling point of water. You may know what these are on the Fahrenheit. That's 32 Fahrenheit, freezing point. That's 212, boiling point, right? So obviously there's actually 180 between boiling and freezing on the Fahrenheit and only 100 between boiling and freezing on the Celsius. That's why I said earlier that Fahrenheits are great, because there's twice as many squeezed into the same space, so it's twice as accurate, right? Okay. But that's not how Fahrenheit set up the scale. Remember, he did set up a 0 and 100 Fahrenheit 100 division scale, just like Celsius, but Celsius was smart. He chose the boiling and freezing points of water, things that are easy to replicate, right? What did he do? Well, think about it. When you have a temperature, you're around 100 degrees C, right? Okay, so that's where when you have a temperature around 100 Fahrenheit, that's what I should have said, right? So that's where 100 Fahrenheit falls, right? It's around 30 something degrees C. But 0 Fahrenheit, which is down here, is slightly less than the freezing point of water, right? So this comes to what science was like back in the day. Back in the day, when you make ice cream, how did you do it? You put ice and water and salt into a bucket, and you put a bucket on the inside with your cream and you stir it around, right? This ice, salt, water bath gets down to 0 degrees Fahrenheit. So Fahrenheit set his coldest lab temperature as 0 Fahrenheit, which was an ice, salt, water bath back in the day. So this is like, years and years ago. Okay, so that was his 0. Reasonable, right? It's kind of hard to make a perfect salt, ice, water bath, so it's not a popular thing to do. Okay, but that's what he set to 0. And then he had to pick something that was close to human body temperature as 100 Fahrenheit. And you know what he picked? He actually picked a pigeon, right? So he actually, now use your imagination, how did he measure the internal temperature of a pigeon? Weird, right? So he actually was sticking a thermometer actually in a pigeon and saying, oh, that's defined as 100 Fahrenheit. Is that an easy thing to do every time you want to measure temperature for an endpoint? No. So, that's why it dropped off, because it's hard to calibrate a Fahrenheit thermometer using 0 and 100 Fahrenheit as endpoints. You can set it up. You can use the boiling and freezing points of water, just 32 and 212. That's what people do now. But back in the day, 0 and 100, it was kind of hard to get. Okay, so here is a summary. Okay. The freezing point of water, 32 Fahrenheit, 0 degrees C, 273 Kelvin. There's 100 kelvins and 100 Celsius between the boiling and freezing points of water, which is 100 degrees C and 373 respectively, okay? 100 divisions between boiling and freezing on Celsius and Kelvin, 180 between boiling and freezing on Fahrenheit. That's why you've crammed nearly twice as many divisions on the scale, so if you measure to the nearest whole degree, it's almost twice as accurate, which is why I like Fahrenheit for everyday use. Okay, if you go all the way to the bottom, there's a break there. Absolute 0, no molecular motion, no temperature, 0 Kelvin, so that's why it's called an absolute scale, okay, because it starts at 0. And these are called degree scales or relative scales because they have negative numbers, okay. Lowest possible temperature in Fahrenheit is minus 459, 273 Celsius, okay. Now, this is just for fun, okay, this is just for fun. Sometimes you are asked to turn Fahrenheit to Celsius, Celsius to Fahrenheit. This is in everyday life, right? So I want to show you how to do that real quick, okay? So if we look at the two scales, they're offset by 32 degrees. So at freezing, they're offset by 32. And then there's a 180 to 100 ratio for the same distance, if you like, okay? So let's write that down. Okay, so degrees F, 180 degrees between boiling point, freezing point of water. Degrees C, 100 degrees between the boiling point and freezing point of water. That means there's a 180 to 100 ratio. For every 180 Fahrenheit steps I take between boiling and freezing, I only take 100 Celsius steps. If I think about that, that's an 18 to 10 ratio. Oh, wait a minute, divide by 2. That's a 9 to 5 ratio, okay? So for every 9 Fahrenheits I rise, I only go 5 degrees C, okay? It's like the rungs on the ladder are further separated on the Celsius, right? It's a bigger gap, so I only need 5 of them for every 9 on this one, okay? So that's the ratio, right, between the step sizes. And then I have a plus or minus 32 offset, because 32 Fahrenheit is 0 degrees C. So at freezing point of water, it's off by 32, right? So these numbers, 32 and 9 over 5, or 5 over 9, 9 to 5 ratio, this is where they come from in these formulas, right? So if I want to use Celsius to get Fahrenheit, I'll just make sure I get it right. So there's your offset, there's your ratio, right? That's why that comes in. And now I don't like what they do in the book. In the book, they say 9/5, 1.8. Yeah, well, it is 1.8, but it doesn't tell you where these numbers came from. It's referring to the offset, the step size difference. Okay. If I just rearrange that, degree C equals 5/9. Use Fahrenheit minus 32. You can just rearrange it. Okay. So you don't need those, okay? I'm not going to ask you to convert Celsius to Fahrenheit on the test or anything like that. It's always going to be Kelvin and Celsius, okay? But in everyday life, this is the relationship between Celsius and Fahrenheit. Then if you want to go to Kelvin, you just add 273, right? From Celsius. Okay, so a quick job for you here, okay? 0 degrees C, 10 degrees C, 22 degrees C, 40 degrees C. These are various kind of temperatures we see in our lives, right? Work out what the Fahrenheit and the Kelvin equivalents are for each one, okay? So use this equation, and then once you got the Celsius, just add 273 for Kelvin. All right, pause there. Okay, you're back. So 32, 50, 72, 104, 273, 283, 295, 313. Okay. All right. Now, extra credit. When I look at this graph, I'm kind of reminded of the tortoise versus the hare, right? Celsius has the bigger step size, if you like, but 0 and 32 are offset. So 0 Fahrenheit's about there. It's a bit lower down, right? So let's pretend that Celsius and Fahrenheit are racing to absolute zero from 0 Celsius and 0 Fahrenheit, right? So Fahrenheit gets kind of a head start, right? But Celsius moves more quickly, so it catches up. And it gets to some temperature where they're the same, okay? So my question for you is this, extra credit, email me, right? What temperature is the same on the Fahrenheit and the Celsius scale? Right? What temperature is the same on the Fahrenheit and the Celsius scale? If you look it up, give you 1 point. If you do me a bit of algebra, right? So put C in here and solve, right? Okay. You can use a bit of algebra. You can use to solve, right? So if you can solve it with a little bit of algebra, 2 points. Okay. All right. Next one, density. Density. All right. So talked about it a little bit. Density is a measure of how much stuff, and stuff is mass, in a fixed volume. Every time you go to the supermarket, you see people doing the density dance. What do I mean about that? You ever seen them in the fruit section? So you see people holding a couple of oranges going like this, right? What are they doing? Well, the oranges are about the same size, and they're trying to figure out which one's heavier because the heavier fruit has more juice in it, right? So heavier for its size is more mass in the same amount of space. It's denser, okay? So things that are dense weigh more for the same size, right? So think of a phone booth back in the day when we were students. We used to try and get as many people in a phone booth as we could. Don't know why. So 1 person per phone booth is a low density, but 20 people in a phone booth, 20 times denser, 20 people in the same space, right? So density is a measure of the amount of matter, grams or kilograms, present in a given volume of material. Okay, students per phone booth, grams per milliliter, grams per centimeter cubed, kilograms per meter cubed. Okay, how much mass in how much space, right? Well, the amount of matter is, of course, mass. So the SI unit, we did this one earlier, mass over volume, equals kilograms per meter cubed. Fair enough, that's the official unit, right? If we did that, we get numbers like this for everyday objects, right? Really, really, really low numbers, yeah? So we don't typically use the true SI unit for measuring and recording density. We use something else, okay, which gives us nice numbers. 0 for a theoretically pure vacuum, right? So no mass in a given amount of space is density 0. Up to 20 something for the densest thing on this planet, right? Okay, but the units are this. They are mass in grams So you weigh whatever it is in grams divided by the volume in milliliters or centimeters cubed, right? So the units are grams per milliliter, and that's usually for liquids, because you measure liquids in milliliters, or grams per centimeter cubed, and that's usually for solids. So if you measured the volume of like a wooden block or something, you measure the centimeters on each side, and you'll get the volume in cubic centimeters, okay? So therefore, this goes down here, grams per milliliter or grams per centimeter cubed. They are interchangeable, okay? They are interchangeable, bring that up. You can use either, okay? You can use either, okay? Now, extra credit density, as I mentioned, the numbers run from 2 to 20 plus something, right? Grams per centimeter cubed. What's the densest object on Earth? Don't give me no black hole or neutron star. I can't get that at Joule. Okay. What's the densest known material on this planet, right? Look it up. Give you a point of extra credit if you tell me what it is. Give you a clue, it's a metal. It's from the periodic table. All right. So the densest known material, what is it? What's its value? Okay. Now, density math, here's an interesting thing. Okay, here's an interesting thing. So for density math, we have like a parent equation, density is mass over volume. If you did a little bit of algebra and just did some cross multiplication, volume is mass over density, and a little bit of equation again, right? Mass equals density times volume. All right. So there are 3 versions of the equation. If you like doing algebra on the fly, you can just quickly derive that from what I call the parent equation. Raise your hand if you like recreational algebra. No one, right? Not many people like recreational algebra. So I do have a little trick for you, right? This was shown to me by a student in my first ever chemistry class at JJC. I thought, wow, that's awesome, right? I call it the pyramid, call it the triangle, whatever you want, right? So just get the parent equation and write density is mass over volume, and write it like that, right? Okay, so that's my little triangle I created. Density is mass divided by volume, and then just cover up the thing you want to find, right? I want density. Oh, it's mass over volume. I want volume. Well, it's mass over density. I want mass. Can you see it? Density times volume. Okay, so that's a nice little trick. And whenever you have a 3-variable problem, this works. So later on we'll do molecular weight, grams and moles, which will make chemistry conversions easy, and then concentration, moles and liters, which will make those calculations easy too. All right, so what I want you to do, this is kind of a nice little question for you here. Okay, do the first part and then we'll discuss it, and then we'll do the second part, right? So when we do it, you know, it's always a nice procedure, right? So density, mass, and volume. Write your variables in the side, right? You know it's a density problem, right? So 23.5 milliliters, so the volume's 23.5 milliliters of a certain liquid weighs 35.062 grams. These are really, really good numbers. This will come off a balance in your chemistry lab because the balances are expensive and they can measure accurately weight, right? Whereas volumetric glassware usually goes to the nearest tenth of a milliliter, so it's not as good, right? So think about that. That has 1, 2, 3, 4, 5 sig figs. That only has 3. At the end of the day, we'll have 3 sig figs, right? So what's the density? Density equals mass over volume. We use grams and milliliters, so 35.062 grams over 23.5 milliliters. Give me all the numbers that come out of the calculator, right? So 35.062 divided by 23.5 equals 1.492, and then a bunch of zeros, grams per milliliter. Okay. Now, how many sig figs does the answer have? Well, that has 3. That has 1, 2, 5. Only as good as your worst measurement. So 1.4, don't round up, 9 grams per milliliter. That's the answer. Fair enough. So that's the density of the liquid, right? Now, here's the catch, right? So what mass will 20 milliliters of this liquid have? Key word in that sentence is this. Because density is what's called an intensive property. It doesn't matter how much stuff you have, its mass divided by the volume is always the same number, right? So if I have a little lead BB, I weigh it, divided by its volume, I get the density of lead, right? If I have all the lead on the church roof, take the mass by the volume, it's the same density, okay, because something twice as big weighs twice as much. So the ratio is always the same if it's a pure thing. Okay, so pure materials, if you look in the back of the book, it's a fixed number for every pure material. In fact, the densest known material you're going to tell me the number for, it doesn't matter how big or small that is, that's its density, right? Okay, so because we know that, we can write it in now into a second problem, density, mass, and volume. This liquid has a density of 1.49 grams per milliliter, has a volume of 20 milliliters. What's its mass? Okay, mass equals density times volume, right? Nope, density times volume, right? So, density, 1.49 grams per milliliter, and keep those units in there, times 20 milliliters. Units cancel. 1.49 times 20, that's got two significant figures, so the answer has two sig figs. 1.49 times 20 equals 29.8, round up, 30 grams. 30 grams is the answer. Okay. All right. Now, just a couple of minutes left before the timer goes off. I'm actually going to probably keep going and just kind of edit the two videos together. That's probably the best way to do it, isn't it? Okay. All right. So as soon as that timer goes off, I'll stop and then I'll kind of start again. Okay, so applications of density. Yeah. So density, remember, is always mass over volume, right? Okay. The question really is, well, how do we find the volume of certain objects? Okay. Mass is easy, just put them on a balance, right? So mass is always easy to find, but in practice, how do you find volume? Okay, there's several ways you can do it. If you have a regular object, and we saw this earlier when we talked about a cube, the volume of a cube is length times width times height. Okay, so if you have a regular shaped object, it's easy, you just use the equation. If you measure the length of each side in centimeters, you cube it up to centimeters cubed. So that's why solids have centimeters cubed as a volume. So if we go cube, all right, find this corner and go in like three different directions. Those are called orthogonal directions, right? Volume is length times width times height. Remember, density, grams and centimeters, right? So centimeters times centimeters is centimeters cubed, fair enough. All right, so that's how we find the volume. So we bust out a ruler, measure the length, width and height of our cube, multiply them out, we get a volume in centimeters cubed, weigh the darn thing, mass over volume. Okay, now a brick is basically a cube that's been stretched. It has the same equation. Okay, you can even bang it into a really kind of thin foil, right? If a rectangular foil, real thin, that's still a brick shape, right? Same equation, length times width times height, centimeters cubed again. Fair enough, right? Last two, they're about to run out of time. So I'll stop and then I'll talk about the sphere, okay? So, all right, back. So spheres, ball, right? So think of like, you know, like almost like the Earth, right? Think of lines of longitude there, okay? Now, when we have anything with spherical symmetry, yeah, okay, it has a radius. So if I pick the center of the Earth and go to the surface, that's called the radius, yeah, okay? And equations for volume of things with circular symmetry, cross sections, always have the radius as a variable, right? So you may or may not remember the equation for a sphere. It's actually volume equals 4 pi r, if I can remember, cubed, that's right, over 3. Okay, so find the value of the radius, cube it up. So you measure radius in centimeters, centimeters times centimeters times centimeters, centimeters cubed. These are all constants, pi, 4, and 3. Okay. All right. Now, bit of fine print here. Say you work at the ball bearing factory and you have to figure out the density of the ball bearing is coming off the line. Do you cut every single one of them in half so you can find the radius? No, because the diameter is 2 radius. So you just get the calipers and measure the diameter and divide by 2. Okay, so diameter divided by 2 is the radius, right? All right. Finally, cylinder or disc. So if I think of a a cylinder. All right, I have a circular cross section, and then I got a certain length or height, right? And that's the radius right there. So think about it. If you think about the volume of a cube, you work out the area of a face, length times width, and then you times it by the other dimension, the height, right? So if I work out the area of a circle, which is pi r squared, and then multiply it by how long it is, I get the volume, right? So that's it. As long as the radius and the length are in centimeters, we're good, right? Now, that works for something like a roller carpet, right? Now, if you've ever been to Caputo's Italian market in Naperville, right? Brilliant deli, yeah. They got all these exotic kind of Italian meats hanging there, like these big carpet rolls of meat, right? And I'm really tempted to kind of go in and snip the wire and just run off with the big carpet of meat, but that's the fantasy situation, right? So what happens is they get the meat down and they cut it into these little coin shapes, don't they? And a coin shape is just a very short tower, all right? So a rack of quarters to 1 quarter, it's the same equation, right? So instead of the length of the carpet or the height of the tower, you just have the thickness of the coin, right? So that is the same, okay? It's the same equation. So L is just short there, okay? Works the same. So density is real easy. Find the volume of the object by using the equation. Measure the mass on a balance, divide the two numbers. Okay, as long as you're in grams and centimeters cubed, you're good. All right. Now, here's a weird example. All right. So, one of my favorite films is a film called 21. If you ever get a chance to watch it, watch it. It's about a college professor, a mathematician, who teaches his students in the math club to get really good at blackjack, because blackjack can be outsmarted because it's just kind of a math problem at the end of the day, right? Okay, and then they go to Las Vegas, they get into an adventure. It's kind of a cool movie. Okay, I'm a chemist. I'm not into memorizing cards, right? I am into density, though. Okay, so if you think about it, if you go to a casino and you don't play blackjack, this is all theoretical. If you don't go to a casino, you don't play blackjack, you play craps or something, some dice game, right? If you were able to somehow use some weighted dice that you brought with you, you could kind of defraud the casino, right? And maybe get your legs broken, right? So this is hypothetical, right? So let's assume we want to go and figure out what they make the dice from at the casino, yeah? Now, density is an as-is physical property, yeah? So every material has its own unique density. If you know the density of the dice at the casino, you just look at the density in a data sheet, and you know what it's made from. Maybe it's Lexan or something, right? So here's our unlikely example. So we sneak into the casino with our analytical balance, because no one will notice the analytical balance, right? And you weigh a dice. It weighs 2.65 grams. And you bust out the calipers real quick and measure the width of a dice. And it's a cube, right? So all the sides are the same. 1.2 centimeters. Now with that information, you can actually figure out the density of the dice, right? Give it a shot. Pause there. Okay. All right. So we're back. Density, mass, volume. All right, so the mass 2.65 grams, fair enough. Now the length is 1.25, so is the width, so is the height. So the volume is 1.2 centimeters times 1.2 centimeters times 1.2 centimeters, which equals, if I just look over here, 1.7 centimeters cubed. Density is mass over volume, 2.65 grams over 1.7 centimeters cubed, which approximately equals 1.6 grams per cubic centimeter. Aha! Sig figs. Just we should be good at this now. 2 there, 3 there. I'm going to trim it to 2. Okay. All right. Now, as I mentioned, densities are fixed numbers for pure materials. Okay. When we look at this, this is a liquid, solids. Okay, gases actually have very low numbers. Now think about that. If I have a solid, the particles are packed together really close, aren't they? So there's lots of particles in the same amount of space, right? In a small amount of space. If I have that same amount of space for a liquid, they're further separated. So there's less of them in the fixed amount of space. And then with the gas, there's even less. So generally speaking, solids have the highest densities because they're packed the tightest. Liquids a little bit lower density because they're slightly separated, and then gas is the least dense. Okay, and we kind of see that in the numbers here. Okay. It also, of course, depends on the individual mass of the atoms. So something like gold or lead, which is low in the periodic table, each atom weighs a lot compared to lithium or aluminum or something, which weighs less. Okay. So, aluminum is used for aircraft. It's got a low density for a metal, whereas lead used in fishing weights is 11.4, so it's much denser, right? Because the individual atoms are much heavier. Okay, but the packing's about the same. All right. Now, finish up the packet with this kind of fun last slide here. Okay. Now, David Letterman, right? Back in the day, back in the 90s, David Letterman had a popular TV show. Maybe you've seen the reruns, okay? And on his segment, well, on his show, he had a segment called Will It Float, okay? And in this segment, he would put some weird object into a container of water, and him and Paul, his counterpart, would decide, will it float, yes or no, okay? And instead of me telling you about it, why don't I just show you? Okay, so I'm gonna, for academic purposes, it's interesting, you can kind of steal anything from a book or TV or media if it's for teaching purposes, so I'm okay to use this, right? So I've got a video of David Letterman doing his Will It Float with a cheese log, so take it away.
But right now, ladies and gentlemen, it's time to play Will It Float. Here we go. And here, by the way, is the home game of Will It Float. Everything contained in one box so you can have just as much fun at home as we do every Friday night here in the theater.
Sure do.
It's the perfect stocking stuffer.
Yes?
If you have strangely shaped feet.
Yeah, that's what I thought.
All right, Alan, what are we playing for tonight?
Dave, we are playing for a cheese log.
Oh, back to you, Dave. A cheese log. And what is the item that we're floating or sinking?
Dave, we're playing for a cheese log.
Yes.
The item is a cheese log.
Oh, I see.
Well, I'm glad to see that it's not only me tonight. I'm having trouble making sense of nothing. All right, so what are we playing for, though?
Dave, we're playing for a cheese log. Back to you, Dave.
We're not playing for a cheese log.
Yes, we are, Dave.
All right.
Make something up, Alan.
What is the item?
Dave, it's a cheese
No, it
log.
can't be. The item that we're floating or sinking cannot be the item we're playing for.
Okay, Dave, we're playing for a monkey.
Oh, good, a monkey, that's it.
Back to you, Dave.
Yeah. Are you happier now?
I feel much better.
All right.
A cheese log, and it's a fat. She's got all that fat. It's got to float.
You say, but it's heavy. I say it's going to sink.
You say it's going to sink?
Yes.
All right, bring up the deal and let's play Will It Float. Here we go, ladies and gentlemen. Hi, girls. Nice to see you. How are you? Anytime, dump it in there. And it sinks. That's how we play Will It Float. We'll see you later.
Okay, you're back. So what physical property of a material will determine if it floats or not, right? It's actually its difference in density, okay? So if I got a lead weight, you know a lead weight sinks, right? Its density in water is, well, its density by itself is 11.4, right? Water's 1.00, right? But if I look at something like charcoal or wood, right? So let's pretend charcoal's wood because it typically is, right? Wood floats, right? 0.57. Do you see how they're stacked? They stack in order of density. The most dense at the bottom, the least dense at the top. Okay, so when we have things of different densities, the most dense will sink to the bottom and they'll stack in order of decreasing density. Think about the planet Earth for a second, right? We have the molten core. Iron, 7 grams per milliliter. Then we have like molten rock, 4 grams per milliliter. Then we have the ocean, 1.2 grams per milliliter. And then we have the atmosphere, 0.001 grams per milliliter. They've stacked, okay? So we see stacking. So if you have things of different densities, the thing at the bottom will be the most dense, the thing at the top will be the least dense, and they'll stack in order. Okay, so my question for David Letterman is, well, what physical property of a material determines if it floats if it is less dense than water? So things that are less dense than water float on top of it, right? Things that are more dense sink beneath it. Okay, so a less catchy segment title would be, will it float? That's really, is it less dense than water? that's the nerd version, right? Okay, so the key fact here is less dense materials float on top of more dense materials. Fair enough. Okay, so this brings me on to a couple of kind of interesting concepts, right? Here's a battleship. Battleships are made of iron, essentially steel, right? Yet battleships float on the water. Wait a minute. 7.8 grams per cubic centimeter is the battleship. Let's just draw it, right? Water's 1.2. Why does the thing that has a density of 7.8 float on top of the thing that has a density of 1.2? Weird, right? Do you know why? Because the battleship isn't entirely made of steel, is it? It's basically a honeycomb of air, right? So inside there's lots of rooms. It's mostly air, actually, with a steel shell. So the battleship, collectively, with all the air and everything else trapped inside, has a density of less than 1.2 grams per centimeter cubed. How do you think a battleship? Here's a submarine, right? You put a hole in it. Now, if you're a big fan of history and you like the History Channel, they always make a big fuss of whether a torpedo strikes a ship below the waterline or not. A bit like the Titanic, the iceberg hit it below the waterline. That was important, right? Because it makes a hole, right? So when torpedoes hit battleships, they don't explode them. That's kind of Hollywood, right? They just make a hole, right? They make a bang, yeah, and they make a hole in the side. And what goes in that hole? Water. And then I've got a steel and water mixture, which is more dense, so it sinks. So battleships float because they've got air inside. When they're torpedoed, those air pockets fill with water, and they become denser than the surrounding water, they sink. Okay, when people scuttle ships, you hear of scuttling ships, sinking them on purpose. There are basically plugs in the bottom which they pull, and the water floods in. Okay, so that's battleships. Dating advice. It's been a long time since I went on a date, but here's a cocktail, right? Now, when I went to Ruby Tuesdays, I think there's a couple of them still left. You can get this thing. It's called the Goldfish Bowl. It's literally as big as my head, right? And you're supposed to kind of have two people drink out of it, right? And it's kind of a two-layer cocktail like that, yeah? And one of the layers is juice, and one of the layers is vodka or something, right? And let's have a scenario, right? So you're out with this creepy person, okay? And in this cocktail, there's a straw that sucks liquid from the bottom layer, and the other person drinks from the rim, right? Now you don't want this person chasing you around later, right? So densities, right? The juice is essentially water. The alcohol is alcohol, right? And you can look on the chart here and find the densities, right? So which is denser? Water. The juice is at the bottom, right? And the alcohol's on the top. Interesting. So remember, you want to get a quick getaway later, you actually suck through the straw and that person drinks from the top and then you can get away. All right. So good dating advice, maybe. I don't know. Now, last thing, then we're done. What we're going to do, remember that we can put things into a container and they'll stack in order of density. It doesn't matter if they're solids or liquids, it's just the density that's important, right? So look back at the previous table. Okay, sketch what would happen if you put ethanol, mercury, and water. So you'll have 3 layers of liquids, right? Oh, yeah, 1, 2, 3, right? 3 layers of liquids, and then a lead BB, a gold ring. Okay, so throw them all in and just put them where they would be. Okay, pause there. Okay, you're back. Of those liquids, mercury is the densest, right? I'm looking over there, Hg 13.5 grams per centimeter cubed. Then, just like the chili cocktail, water, 1 gram per milliliter, and alcohol, 0.7, what's that one? 7.8 grams per cubic centimeter. So mercury at the bottom, water, then alcohol, right? Now let's do the thought experiment. We throw in a BB, right? A BB is lead. Lead, if we look at our numbers, where's lead? 11.4, right? So put it in. Is it denser than the ethanol? Yes, it's going to sink to there. Is it denser than the water? Yeah, it's going to sink to there. Is it denser than the mercury? 11 versus 13. No, it's not. So it actually sits on top. It's going to float on the mercury. Interesting. Then we throw in the gold ring. Gold ring goes in. Gold, pretty dense, right? Gold, where is it? 19.3. 19.3, yeah, bigger than 0.78, bigger than 1, also bigger than 13, so the gold ring sits at the bottom, okay? So you may be asked to sketch something like that. What would the order of stacking be based on density? Works for the planet Earth, works for cocktails, works for questions, okay? So stop there. Now, hopefully you've got all the information you need to answer your density lab, okay? I'll also do a pre-lab for the density lab, so watch out for that too. Okay, see you next time.